Time for a pop quiz. Brace yourselves, everyone. Oh yeah? Prepare to be iterated.
Hello everybody, welcome on in. My name is Pen Center. Thank you for the raid gold. We're just about to start some machine learning tonight. If you hear food processing in the background, David is just cooking dinner. There's nothing I can do about that. Thank you for breaking my GPU gold. You're the best. I see you, Fem. I see you. How you doing? And thank you very much for the follow, Joseph. Fem, I think that is correct. There's your QED point. Hopefully that doesn't break stuff.
Huh. Nicely integrated.
I'm pretty sure it's just my filter that's breaking everything. What am I getting a gun? I don't know. They call that targeted marketing. Because Twitch, true. True. Okay, let's take the filter off and see if that helps speed things up around here. Hello. Hello? Stream Deck, what the fuck? I would see that as a compliment, absolutely. Why is Stream Deck not working? What the filter must stay? Sure.
Look at me.
Jeez. There we go. Okay. Filter gone. We're in math mode. That was definitely not smooth at all. Yeah, there's been so many updates. Like Stream Deck had an update, OBS had an update, frickin' Windows 11 has an update. Like everything got updated and everything's broken and it's frustrating. Oh well. So, the last time we were together doing some machine learning, we were looking at, we were doing linear and quadratic discriminant analysis. We finished that chapter, so I think I'm going to move into the next chapter of the textbook, which is, I have no idea what this is. I've heard of support vector machines, but I literally have no idea what it is. Who is cooking? Oh, wait, that's my music. Okay. There we go. Now I'm not looking at an orange screen. One day you'll stream and share my frustrations. Do it tomorrow, please. I want to watch some chill chess streams. Yeah, seriously, Windows 11 has been such a pain in the ass. Ooh, yeah, everyone's breaking stuff. Moved in today. Oh, you're in your new place? Oh, nice. Nice. Congrats. Congrats. Wait, do we have a soundboard? Do we have a soundboard? Yay. Jeez. Holy crap. Stream Deck is so delayed right now. This is wild. Yeah, bye, Reese. Hi, Reese. Bye, Reese. I closed the door and he was like, I'm getting out of here. But I think he got scared of everything in the kitchen, too. Alright, let's pull this down a little bit so I can focus in here. Yeah, you pet that couch. You pet that couch. You got a separate room for studying. Sweet, gonna set the whiteboards later this month. Later this month? It's November 2nd. Don't say later this month. Do it now. I love petting couches. Petting couches and condom ads. It's the best Sunday ever. Okay, chat. I literally have no idea what naive Bayes is. I barely know what Bayes' theorem is. I think it has something to do with conditional probabilities. I'm not a statistician. And then there's something here about support vector machines. People talk about this stuff all the time, but I literally have no idea what it is or what the point of support vector machines is. So it's going to be a bit of... This chapter will be a small adventure, I think. So it looks like we're going to cover working with naive Bayes, understanding the support vector machine algorithm. That sounds fun. And then tuning many hyperparameters simultaneously with a random search. Working with the naive Bayes algorithm? Yeah, that's true. It might be different than the probability thing. That's true. Oh, all your whiteboards are in Penticton and you don't have a car. Oh, damn. When are you going to be able to go get your stuff? So naive Bayes and support vector machine algorithms are supervised learning algorithms for classification. Each algorithm learns in a different way. The naive Bayes algorithm uses Bayes' rule, which is, I think, that conditional probability rule, to estimate the probability of new data belonging to one of the classes. So it's using conditional probability to figure this out, I assume. The case is then assigned to the class with the highest probability. Sure. The SVM algorithm looks for a hyperplane that separates the classes. That's kind of sexy. The position and direction of the hyperplane depend on the support vectors. Oh, that's interesting. So this is kind of... I'm getting a sense it's kind of like a generalized version of like... I'm going to be generalized like linear discriminant analysis? Because doesn't linear discriminant analysis find a plane for us? And it finds two like perpendicular vectors that basically get oriented in the best direction to separate the classes. So what we're doing here is we're looking for a hyperplane. So this is a surface that has one less dimension than there are predictor variables that separates the classes. That's crazy. So it keeps it pretty much in the same dimension. Almost in the same dimension that we're working in. So LDA takes whatever dimension we're working in and smushes it down to 2 dimensions and finds a plane, or sorry, not really a plane, I guess, but yeah, I think it's kind of like a coordinate system in some sense, right? Like it finds a coordinate system for us that'll orient everything and separate the classes maximally. So this is it feels kind of like it's doing the same thing. It's looking for a hyperplane. Huh. Yeah, that's fair. Later this month or the next, not sure. Oh, okay, so yeah, if you're relying on family, may not be the most reliable. And it's an hour away. It's a long way to drive. I'm lost. W the words in the text. What? Yeah, that's the sense I get here too, Joseph. It kind of feels similar, but we're not collapsing it as much. Yeah. So in this case, you're right. We're not reducing the dimensionality. We're actually finding something that'll slice through all the classes. So that's kind of cool. That's really cool. The position and direction of the hyperplane depend on our support vectors. Probably perpendicular vectors. That would make a lot of sense. Okay. Blah, 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 blah. Okay. So the naive Bayes and SVM algorithms have different properties. We might actually go. I kind of want to look at the statistical shit here too. So we might like read a little bit tonight, and then I might pop into that that statistics book that we have as reference. So for those of you that are new, if you go into the elements and you scroll down into the elements into the machine learning section, we have all of our resources popped up in here. So all of our books and things like that are popped up in here. Whenever I need help for stuff, I post things in here too. So if you're looking for all the references, we do have it in the Discord. In the Discord. Okay, so naive Bayes and SVM algorithms have different properties that make each suitable in different circumstances. So for example, naive Bayes can mix both continuous and categorical predictors. So that's interesting. So the linear discriminant analysis, all of our predictor variables, basically all of our columns had to be numerical and continuous, I think. Or at least had to be numerical, if I remember. At least numerical. They couldn't be categorical. So this says naive Bayes can mix both continuous and categorical variables, which would be super helpful because that happens a lot. While for SVM, categorical variables must be first recoded into a numerical format. Okay, so categorical. So basically, we're taking categories, we're assigning it 0 to n, or n-1, or whatever it is, and then that'll help us get SVM sorted. So that was kind of similar to LDA, the linear discriminant analysis. We had to do the same thing. Is everything okay out there? Do you need help? Do you need help? All I heard was Mayday. Oh, okay. Be right back. Be right back. Hey Stuart, how's it going? This song, you're saying categories as in category, not category theory, if that's what you're wondering. As an avid organic chemist, LDA sends me into a different thinking space. Sure. LDA. Wait, what's LDA in chemistry? Is that like a drug? No, that's LSD. Whoops. Wait, why are you using Discord in your browser? Just download the app, yo. Okay, so blah, blah, blah. So SVMs are excellent at finding decision boundaries between classes that are not linearly separable by adding a new dimension into the data. Okay, I don't know what that means, but hopefully it'll explain it a bit more. A naive Bayes algorithm will rarely outperform an SVM trained on the same problem. Interesting. But naive Bayes tends to perform well for problems like spam detection and text classification. They're saying models trained using naive Bayes also have a probabilistic interpretation. For each case on which the model makes predictions, the model outputs the probability of that case belonging to one class over another, giving us a measure of certainty. Okay, this is useful for situations which we may want to further scrutinize cases with probabilities close to 50%. And SVM doesn't give us probabilistic, it gives us geometric interpretations. Oh, okay. So they're very different kind of things. They partition the feature space and classify cases based on which partition they fall within. Right. So here's probably something that's important. So it says the support vector machines are more computationally expensive to train than the naive Bayes model. So if naive Bayes model performs well, there's really no reason probably to use SVM is what they're saying. So by the end of the chapter, you'll know naive Bayes and SVM algorithms, blah, 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 blah. Okay. Yeah, so let's try to figure out what the hell this is. In the last chapter, we did see Bayes' rule. I mean, just for sake of maybe review, let's take a look at that. Bayes' rule. Is that Bayes? Yeah, I guess so. So it's saying that I can get to the probability of A given B using the probability of B given A, and the probability of A, and the probability of B. So it's just a way for us to go back and forth between conditional probabilities if we know one over the other one. Well, a very strong base. Oh, okay, okay. Sent me an e-transfer for the session with Uriah. Send you pay stuff. Yeah, sounds good, man. Sounds good. LDA is linear discriminant analysis in machine learning. So there's LDA and QDA. QDA is the quadratic one. So I showed how discriminant analysis of blah, blah, blah. The naive Bayes algorithm works in exactly the same way, except that it doesn't perform dimension reduction like discriminant analysis will. And it can handle categorical and continuous predictors, right? So that's, to me, that feels like a win, right? If I know I have variables, right, or predictor variables that I'm using that are categorical, naive Bayes will take care of that already. So that's super nice. Imagine 0.2% of the population have a unicorn disease. That would be terrifying. Can you imagine just like waking up and having a horn on your face? God damn. Symptoms include obsession with glitter and compulsive rainbow drawing. That's what?
Bruh.
The test for unicorn disease has a true positive rate of 90%. If you have the disease, the test will detect it 90% of the time. When tested, 5% of the whole population get a positive result from the test. Based on this information, if you get a positive result from the test, what's the probability that you have unicorn disease? Ah, okay. I wonder if we could maybe... I'm not going to look at the answer, but let's ponder about that for a hot second and see if we can figure out what this... I've never really taught or used Bayes' theorem for anything, so I'm a little uncertain what that would look like. Unfiled. Wait, do I not have... Okay, never mind. We'll just do this. We'll call this... I thought I had a machine learning one. Just call it NL. And we like the grid lines around here. Let's get some grid lines going in. Okay. Let's pull in this as well. Just paste picture. Oh, son of a gun. Son of a bitch. All right, so what information do we have? So the probability of having the disease is 0.2%, not 20%. So The test has a true positive rate of 90%. So what does that mean? If you have the disease, the test will detect it 90% of the time. So that is... B given A, right? This is so we're looking at probability of B given A being 90%. Is that true? Right, so the test will give me a 90% detection rate if we know we have the disease, right? So this is test positive given we have the disease. I think that's right. It's a very scary disease, yes. Accurate. Okay, so when tested, 5% of the whole population get a positive result. Is that B? So the probability of positive is 5%? Oh, I hate new OneNote. New OneNote sucks. I think that's probability of B, isn't it? Right? Is 5%? I just want to write this down. So this is like B is going to be a positive test, right? So if we just blindly test people, we have a 5% chance of testing positive, but if we know they have the disease, they have a 90% chance of testing positive. Based on this information, if you get a positive result, what is the probability you have the disease? So what's the probability we have the disease given we get a positive result? So yeah, we're trying to calculate A given B, right? So we want the probability that we have the disease given that we've tested positive, which should be 0.9. So B given A times probability of A over probability of B. So they're saying it should be this. So like 3.6%. Does that make sense? Hey, Uncle Bill, how's it going? Uh-oh. I have no idea if that makes sense. I can't really understand what that looks like. It seems really low, though. Oh, no, that kind of makes sense, right? If we blindly test people, it should be 5%. So if we get a positive result, some of those 5% will not have the disease. So Bayes is just telling us it should be less than that 5%. Okay, I think that kind of makes sense. So let's see if... So we've done all this work, but let's just kind of see how they rewrite it. So our likelihood is 90, blah, 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 our power, blah, blah, blah. You can see all the values illustrated in figure 6.1. Now we simply sub these in. Ba, 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 ba. Okay, well that's just them needing a condom over talking about Bayes' rule. So let's see. So prior, likelihood, evidence, posterior. I have no idea what they're talking about here. I also like that they put a frickin' horn On the unicorn disease, that's funny. Oh, I see. So they're trying to divide this up into true positives and true negatives and sum up some of the positives or something like that. So if... Oh, I see. So they're saying that if 0.2% of the population has... Right, multiplying that by 90% and or 10% will give us the true positives or the false negatives. Right, so there's a 0.18 true positive rate. And they divide that by 5% positive to get the 3.6. Right, the baseline. Okay, I see. If we multiply this to get the false negatives, we don't care about those. But wait, are there also not going to be people coming? So don't. Oh, I see. None of these people we care about down here because we know they don't have the disease. So these people don't have the disease. How are they getting these numbers? 4.83 and 95.17. Did you say the baseline or the baseline? Stop. Stop. Stop it. Bruh. I get the logic up top. The up top logic kind of makes sense to me. I don't know where they're getting this 4.83 and 95.17 though. That's weird. Okay, so how do we use it for classification? Imagine you have a database of tweets from the social media platform X, and you want to build a model that automatically classifies each... They still call it a tweet, even though it's X. The topics are politics, sports, movies, or other. You create 4 categorical predictor variables, whether the word opinion is present, whether the word score is present, game, and cinema. Okay. Makes sense.
What's your name, sir?
My name's Deez.
Deez what, sir?
Deez. Stirring the beast, look into my eyes. Not telling the things you were laughing about behind my neck. There's your necessity.
Sir, let me see your ID.
Ah, shucks.
Oh, shucks. How you doing, Deezy? Welcome in. If we're really trying to build a model to predict tweet topics, we would need to include many more words in this. True. For each of our 4 topics, we can express the probability of a case belonging to that topic as P topic given words. Right. Okay, so based on the words that we're getting out of the tweet. Got it. Okay, so there's... Yeah, okay, that makes sense to me, right? So we post something, we're scanning those tweets to see if opinion, score, game, or cinema are present, and then we're matching that back up to the topic because we actually have the tweet and we can figure out what the topic is. So we should be able to calculate some stuff given the words, right? I guess it could go the other way around too, right? Like in the training data that we have, we know the words that are present and we know the topics that are present. So we should, I guess, realistically be able to calculate at least one of these probabilities. Now we have more than one predictor variable. Oh god, what is this? What is this nonsense down here? This username checks out. True. Words topic is the likelihood of a tweet having that exact combination of words present, given the tweet is in that topic. Huh? What? Huh?
Huh?
Is the likelihood of a tweet having that exact combination of words, given that the tweet is in that topic. Okay, fine. We estimate this by finding the likelihood of having this combination of values individually, given that the tweet belongs to that topic, and multiply them together. This looks like it's gonna suck. Okay, so it's really just like a weird expansion of probabilities. They're doing all 4 words, right? So given that we know the topic, what's the probability opinion is in there, or score is in that tweet, or game is in that tweet, or cinema is in that tweet, they're multiplying all of that together, dividing out the singular probabilities here at the bottom. Fine. So for example, if the tweet contains the words opinion, score, and game, but not cinema, then the likelihood would be as follows for any particular topic. Sure. Now, the likelihood of a tweet containing a certain word, if it's in a particular topic, is simply the proportion of tweets from that topic that contain the word. You're right. That should just be a straight-up division, right? Multiplying the likelihoods together from each predictor variable gives us the likelihood of observing this combination of predictor variable values, this combination of words given a particular class. Blech, gross. This feels like it would get super messy super fast. If I had to like code something like this, that would be wild. So they're saying this is what makes Bayes naive. By estimating the likelihood for each predictor variable individually, then multiplying them, we're making the strong assumption that the predictor variables are independent. There it is. Yeah, okay. Geez, like, honestly, like, looking at... I feel like Naive Bayes is kind of like Mortal Kombat. I'm not gonna lie. I feel like this chapter just might finish me. I mean, I'm sure the coding part of this is going to be easy, but I'm scared to open up the statistics textbook and read this. Okay, so yeah, so we have to assume independence. That's a big assumption. But I imagine independence probably makes covariance matrices very nice. Like, it probably makes the background statistics work super nicely, would be my guess. In spite of this naive assumption being wrong quite often, naive Bayes tend to perform well even in the presence of non-independent predictors. Having said this, strongly dependent predictor variables will impact performance. Cool. Okay, so our predictor variables shouldn't have very strong dependencies on each other. So the likelihood and prior probabilities are fairly simple to compute and are in the parameters learned by the algorithm, but what about the evidence? The probability of certain words? In practice, because the values of the predictor variables are usually reasonably unique, counting the evidence is very difficult. Interesting. As the evidence is really just a normalizing constant that makes all the posterior probabilities sum to 1, we can discard it. What? And simply multiply the likelihood and the prior probability. So the posterior is similar to likelihood times prior. Huh. So they argue that proportionality is good enough to find the most likely class. Sheesh. Can I have an example, please? I don't... We might have to go over to the stats textbook, I'm not gonna lie. I kind of want to see... it's gonna be really hard to read this fucking book, though. Which one is it? Is it this one? Yeah, the hasty book. I'm feeling a little hasty, chat. I hope you're feeling hasty, too. Blah, blah, blah. Give me to the table of contents. Local methods in high dimensions. That's regression. Linear methods for regression. Least angle. Least squares. Linear methods for class. We're doing classification, right? These are probably mostly linear methods. I see. So LDA was in here. Reduced rank. Logistic. Separating. Piecewise polynomials and spleens. Filtering, smoothing, spleens. Spleens? Splines? Spleen? Spline? Do these guys do naive bays? Kernel smoothing methods. That sounds weird. Here, let's do this. What are we looking for? Naive bays. No, it's not even in the textbook. God damn. Is it in the other textbook? Oh, wait. It found one instance of naive bays. Okay, I thought it would be in Chapter 4. Oh, okay. Naive Bayes models are a variant of the previous case and assume that each of the class densities are products of marginal densities. That is, they assume the inputs are conditionally independent in each class. Section 663 is where we want to go. Oh, it's a kernel smoothing method? What? I should probably read this. Kernel density estimation is an unsupervised, but we're doing supervised, though. Damn, I need to take some advanced stats classes. I need a teacher to teach me how to do some of this shit. There's so many weird things that look scary. Okay, the naive Bayes classifier. This technique that has remained popular over years despite its name, also known as idiot Bayes. What? Okay. It is especially... Is that a translation error? Okay, it is especially appropriate when the dimension P of the feature space is high, making density estimation unattractive, right? So they're probably
What's your
talking
name,
about...
sir?
My name's Deez.
Deez
Hi,
what, sir?
Plasma!
Deez.
How you doing?
Into my eyes. Not telling the things you overlapping about me. I'm 99. That you never did.
Sir, let me see your ID.
Ah, shucks.
Oh, shucks, Plasma. Yeah, okay, so I'm assuming here the density estimation unattractive is probably, in layman's terms, saying that the dimension is, like, is too high, right? Or too computationally challenging. So if we assume independence of the distribution, something nice probably happens.
Here we go. Let's
So
see
the
the
individual
solution
class
to your
conditional
advanced algorithm.
marginal densities can each be estimated separately using one-dimensional kernel density estimates.
It's all exponential.
QED chance! Good luck, everybody.
Time for a pop quiz.
Oh, here it is. If a component xj of x is discrete, then an appropriate histogram estimate can be used. This provides a seamless way of mixing variable types in a feature vector. Plasma, look at you. Nicely done. Bam. There you go.
Problem solved.
2 QED points. Hot dog, don't spend them all in one place. Despite these rather optimistic assumptions. Naive Bayes classifiers often outperform more sophisticated alternatives. Let's get rid of this. Okay, so starting from 6.26, we can derive the logit transform using class J as the base. This looks very similar to what we were doing the last time, so stripping this out, and they get something like this. So this has the form of a generalized additive model, which is described in more details in Chapter 9. The models are fit in quite different ways, though. Their differences are explored in 6.9. The relationship between naive Bayes and generalized additive models is analogous to that between linear discriminant analysis and logistic regression. Okay, this sounds important. The relationship between naive Bayes and generalized additive models is analogous to that between LDA and logistic regression. Well, what? What? Wait.
Hey, Tails. Why don't people ever pick fights with dinosaurs?
Not this again.
Because they'll get your ass kicked.
Allow me to explain the joke.
No, that's it. Persona! This turn in a fish. Look into my eyes. Not telling the things you love now behind my back.
You're like, oh shit, I was right.
Guacamole. He got a new form too.
Holy fuckamole, you were right, Plasma. The fuck happened there? You did good, man. You did good. This feels important. So naive Bayes and generalized additive models are analogous between LDA and logistics. So we know LDA is a dimension reduction that works on continuous predictor variables. Logistic regression works on categories and develops a curve to help us predict if it's going to land into a particular category. So it works only on categorical predictor variables. But we know naive Bayes can work with different things. It's not a dimension reduction, so I'm really confused at this sentence. Section 445. Maybe it's because we haven't looked at logistic regression yet. So maybe there's more between LDA and logistic regression that I'm a little unfamiliar with. That might be helpful here. Okay, and that's really all they have about naive Bayes, I guess. But why don't we take a look at 445 and see if that'll give me some 445 logistic regression or LDA. Okay, so a lot of stuff. This linearity, oh, I see. So it became a linear kind of problem, is a consequence of the Gaussian assumption. Right, so normal, if things are normal, then this simplifies super nicely, is what they're saying. For the class densities, as well as the assumption of a common covariance matrix. Right, so there was something about covariance, right? Common covariance matrix that was helpful. Was that independence as well? Common covariance matrix? On the linear logistic model, it seems that the models are the same, although they have exactly the same form. The difference lies in the way the linear coefficients are estimated. The logistic regression model is more general. It makes less assumptions. For both LDA and logistic regression, the second term on the right has the log at linear form. I have no idea what that means. I feel like my brain is shrinking the more and more I read these textbooks. I'm just like, there's so much happening, and I cannot wrap my head around what the fuck is going on. The logistic regression model leaves the marginal density of X as an arbitrary density function and fits the parameters by maximizing the conditional likelihood. Although probability of X is ignored, we can think of this marginal density as being estimated in fully non-parametric and unrestricted fashion. With LDA, okay, so that was logistic regression. With LDA, we fit the parameters by maximizing the full log likelihood based on joint density. I still don't understand what the fuck that means. Since the linear parameters of the logistic form are functions of the Gaussian parameters, we get their maximum likelihood estimates by plugging in the corresponding estimates. There's some calculus involved there. However, unlike the conditional case, the marginal density does play a role here. Blah, 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 blah. Just what is happening? This was like that one time when I tried to learn physics, and I was just like, what the fuck? The textbook made 0 sense. I feel like I'm gonna absolutely, after I get through Reese, I'm gonna have to do some more statistics, man. I'm gonna have to do some more statistical learning. This is nuts. Is there a paragraph that will actually make sense? It is generally thought that logistic regression is safer, more robust bet than LDA, relying on fewer assumptions. It is our experience that the models give very similar results, even when LDA is used inappropriately, such as with qualitative predictors. Qualitative. Oh, I see. So, yeah, LDA should be used with quantitative predictors. So there's something about how things are estimated, is basically probably what they're trying to say. So there's a different way of estimating some of the things with regards to logistic regression versus linear discriminant analysis, and somehow the different ways that you make the estimations they're saying that it's very similar when we're looking at naive Bayes versus something else. I forget what we were looking at. They were comparing naive Bayes to something else. Holy moly. Hey MQ, how's it going? Randomly draw a circle around a group of the population and it's an approximation. I guess, yeah. It's an approximation of the population. Don't ask me, I'm researching a probability-based thing and I have no clue what's going on. I know, I love how naive is the academic way of saying stupid. It's true, yeah. It's a pretty big assumption, right? Like, honestly, like, assuming that a whole collection of variables are independent of each other, that's a pretty lofty assumption, right? MQ, we were trying to learn a little bit about the naive Bayes method. I might bounce back to Reese. Okay. I'm not going to do any coding tonight because I'm a little too sleepy for that, but I do maybe want to read a little bit about support vector machines. Or if there's individuals that want to talk about some other kind of math thing, I'm happy to talk about some other kind of math thing for a little while too. We'll come back and we'll do some of the coding stuff a different day. I'm not into coding right now. So strengths and weaknesses. Well, it often isn't easy to tell which algorithms will perform well for a given task. Here are some strengths and weaknesses that will help you decide whether naive Bayes will perform well. The strengths: it can handle both continuous and categorical. That's helpful. It's inexpensive to train, also very helpful. Commonly performs well on topic classification problems where you want to classify documents based on words. That's really helpful. Has no hyperparameters to tune. It's probabilistic and outputs the probabilities of new data belonging to the class. That's kind of important too. It outputs the probabilities of new data belonging to the class. Can handle cases. Oh, it can handle cases with missing data. That's interesting. So the weaknesses are, it assumes that continuous predictor variables are normally distributed, which is not always true, and the performance suffers if they are not normally distributed. It assumes that the predictor variables are independent. Yes, right? That's the naive part, which usually isn't true either. Yeah, it makes sense. I probably won't have a fucking clue what's going on. Yeah, this is my life. My life when it comes to machine learning is exactly that. Your math bio assignment? Yeah, I want to see your math bio assignment. It probably looks freaking crazy. All right, let's do a little bit of reading on SVM and see, maybe try to compare and contrast a little bit. Just send it to me in like a DM or something and I'll show it on the screen. Everyone can cry a little bit before we get off stream tonight. In this section, you learn how SVM algorithm works and how it can add an extra dimension to the data to make the classes linearly separable. I like this. Imagine that you'd like to predict whether your boss will be in a good mood or not. A very important machine learning application. Over a couple of weeks, you record the number of hours you spend playing video games at your desk and how much money you make the company each day. So we have two continuous variables, predictor variables. You also record your boss's mood as good or bad. That's a category. They're very binary. Yeah, there you go. You decide to use SVM to build a classifier that will help you decide whether you need to avoid your boss on a particular day. The SVM algorithm will learn a linear hyperplane that separates the days your boss is in a good mood from the days they're in a bad mood. That sounds fantastic. This is like, I feel like people could actually reasonably use this. The SVM algorithm is also able to add an extra dimension to the data to find the best hyperplane. Huh. I'm kind of curious as to why they would want to add an extra dimension. Okay, so take a look at the data in figure 6.3. The plots show the data you record on the mood of your boss based on how hard you're working and how much money you're making the company. The SVM algorithm finds an optimal linear hyperplane that separates the classes. that is a hyperplane for two-dimensional. For a two-dimensional feature space, the hyperplane is a straight line. Yeah. Three-dimensional, it's a surface. It's hard to picture hyperplanes in form, blah, blah, blah. Okay. So suboptimal boundary, hyperplane support vectors. What? Margin. So support vectors are these two circled pieces of information. Finds a hyperplane that passes through the feature space. An optimal hyperplane is one that maximizes the margin around itself. Ah, the margin is a region around the hyperplane that touches the fewest cases. What? That touches the fewest cases. Huh? Support vectors are shown with double circles. That sentence is weird. I don't like this sentence. That touches the fewest cases. It must be dependent on the margin, then. It must be dependent on the margin. So the margin is a region around the hyperplane that touches the fewest cases. So we just keep increasing it. And we stop when we basically hit a couple of cases, I guess. Right, in either direction. Is that what it is? Okay, looked at that already. So for problems where the classes are fully linearly separable, there may be many different hyperplanes that do just as good a job at separating the classes in the training data. To find the optimal one, the algorithm finds the hyperplane that maximizes the margin around itself. Okay, like I can kind of visually see that. That makes sense. The cases in the data that touch the margin are called our support vectors. Okay, because they support the position of the hyperplane. Huh. I think you've seen SVM visually explained on the Visually Explained YouTube channel. Hey, well, why don't we take a look? SVM Visually Explained YouTube. Oh, right. That's not... Well, one, that's not what we want. And two, you guys won't be able to hear that. So I don't think that's helpful. So let's see if I can find it over here. Yeah, it took me a second to realize that was the name of the channel. Let's see if I can find it. Alright, we'll go into our Elements YouTube channel. We're going to search up Visually Explained.
Testing.
For SVM. Support. Let's just look for support. Playlists. You're gonna have to let me know if this is the let me just get some stuff back up here. Visually Explained. Oh, okay. Is this the YouTube channel that you're talking about, Joe? Excellent. Oh, that's perfect. Oh, maybe it's probably this one. This one looks nice.
In machine learning,
Support vector machine in 2 minutes. It's probably this one.
No, that's a zero vector. Recalculate your stance. Zeta slow to deny me.
in machine learning,
Iterate or get erased, kid. Sign. cosine, tangent.
All right, let's pause the music for a hot second and watch this bad boy. Hello, what? Pardon me? Why is this not piping through the right thing?
Classify into two categories or more. Is this picture of a dog or a cat? Is this stuff going up or down? SVMs or support vector machines are some of the simplest and arguably the most elegant methods for classification. Each object you want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform most fundamental tasks is when you have a bunch of objects that you want to classify into two categories or more. Is this picture of a dog or a cat? Is this dog going up or down? SVMs or support vector machines are some of the simplest and arguably the most elegant methods for classification. Each object you want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is, a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the two categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin, and where the constraints say that points of each category should be on the correct side of the hyperplane. In practice, you don't have to worry about the implementation details of this optimization
lots
problem.
of math. No, go back.
Implementation details of this.
Okay. For all x and c1. Oh, I see. So bigger than 1, smaller than -1 for all x and c2. So c1 and c2 are the spaces, obviously. X's are the data points that we're working with, either the pink or blue points. W and B must be... W looks like a W transpose, so it must be some kind of vector. What does that mean? Max WB, where we're taking the length -2? Is that some kind of like so it's the magnitude of the vector, but why is there a -2 there? What does that mean? We take the inverse root of the magnitude of the vector? Is that what we do? Take the inverse root of the magnitude? And we just try to maximize that, given W's and B's, I guess?
This optimization problem. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. The biggest pros of SVMs is that they are easy to understand, implement, use, and interpret. Furthermore, they are effective when the size of the training data is small. The simplicity of SVMs can also be a problem. In many applications, the points cannot be separated by hyperplane. A common workaround in this case is to A. Augment the data with some nonlinear features that are computed from the existing ones.
Of course.
B. Find a separating hyperplane in this higher dimensional space. And C. Project back to the original space. A clever technique known as the kernel trick allows us to perform all of these steps in a very efficient manner. And now that you know about SVMs, you can use them for face detection, spam filtering, and text recognition. This was SVM in about 2 minutes. Like and subscribe if you like the video, and
got
see
it.
you next
Okay,
time.
so that's why they do the higher dimensional piece. So the higher dimensional piece allows them to fit the hyperplane, then you reduce back to the original dimension set. Okay, that makes a lot more sense. Least squares. Okay, so it's a least squares problem? Okay, well that makes sense. Least squares is like all over the place, man. It's crazy. Cool, thank you for that, Joe. Appreciate it. Okay, so we're saying the support vectors are the most important cases because they define the boundary between the classes. Not only this, but the hyperplane. but the hyperplane that the algorithm learns is entirely dependent on the position of the support vectors, right? And none of the other cases, right? Moving a support vector moves the boundary. Huh? Oh, yeah, I see. So they're taking this one, moving it up, so now this becomes a support vector. That one probably would lose its ability to be a support vector? Oh, I see. And then moving that in changes the position of the hyperplane. Moving a non-support vector has no effect, right? Okay. SVMs are extremely popular right now. Cool. We get to be a part of the in crowd. They are good at finding ways of separating non-linearly separable cases. Like what we saw in the video, right? Where they increase dimension, slice through a hyperplane, and then project back. They tend to perform well for a wide variety of tasks. We now have the computational power to apply them to larger, more complex data sets, right? Because I assume that as we start to increase the dimensionality, things are going to get a little spicy. The downside of SVMs, they tend to be more computationally expensive to train than many other classification algorithms. If you have a very large data set and computational power is limited, it may be economical for you to try cheaper algorithms first and see how they perform. Right. Cool. I guess the support vectors are like the bounds of the hyperplane. I don't know if I'm not sure I agree with that. They're the bounds of the margin. Right? Like they shouldn't fall on the hyperplane, but something about them is interesting. Because moving the support vectors around changes the position of where the hyperplane is. So, but I understand what you mean, right? Like they feel like the boundary cases of like where we're looking, right? Yeah. So I get what you're saying. Totally get what you're saying. The math underpinning how SVMs work is complex. Yeah, it looked a little crazy in that textbook. Some of the basics. You'll often see the equation for a hyperplane given as wx plus b equals 0, where w is the vector negative b negative a1, and x is the vector 1xy, and b is still the intercept. Whoa, hold up. Recall from chapter 4 that the equation for a straight line is y equals ax plus b, where a and b are the slope and y-intercept. We could rearrange this equation to be y equals negative ax minus b equals 0. Sure. By shifting all the terms onto one side. Using this formulation, we can say that any point that falls on the line is one that satisfies this equation, right? So a given a and b, we know how to find a, b, and say x, we know how to find y, or a, b, and y, we could find x. You'll often see the equation for a hyperplane given in the same form. It's linear, but since we're in we're in higher dimensions, w, x, and b have to be vectors, right? Where w is the vector negative b, negative a1, x is the vector 1xy, and b is still the intercept. In the same way that any point that falls on the hyperplane satisfies blah. Yeah, they're using a lot of like very linear examples in the book because it's easy to draw those. And you're saying there's a lot of data sets where we can't do that. correct. So my guess is it would look something like this. Like if I had a data set that looked super funky, like I had like, I don't know. I'm spitballing here, but let's say you had something weird like this, where like it wasn't super clear how to draw a line through this data. What I'm getting the sense of what they would do is they would take this and they would convert this into 3 dimensions, where they would kind of raise or lower some of these things. So they add an extra dimension to this so that they can slice a plane through the data. So maybe they lift all the black stuff up, right? So all the black stuff is up here, and all the red stuff is down here. And they kind of slice a plane through it this way. So they're like, oh, I'm gonna like slice my plane like this way. This is a terrible looking plane. But hopefully you know what I mean, right? So they can kind of slice, so that everything looks like this. They increase the dimension, so all the black stuff is above the red stuff, and then now I have space to slice a plane through there, and find the plane that has the maximal margin. And then what's going to happen when we go to put stuff back together like this? That's the interesting part. So
add a red-black axis, make it orthogonal, project and slice with a hyperplane. Zeta trivial.
Yeah.
And values.
yeah, exactly. So you just, yeah, it's kind of interesting, right? I like the theory is super interesting. I'm curious to know how the math works, but it feels like it's kind of complicated. And then you get, yeah, you must be getting like some kind of projection, and then we're going to be able to kind of map out. So maybe what we would get is we would get kind of a projection where we have, you know, like a kind of like a donut or something like this down here, right? I don't know. I don't really know. I'm trying to kind of learn this, but I can kind of see it. I can see it a little bit. The vector W is orthogonal or normal to the hyperplane. Therefore, by changing the intercept B, we create new hyperplanes that are parallel to the original. Right, we're just sliding stuff around. By changing B and rescaling W, we can arbitrarily define the hyperplanes that mark the margins. By changing and rescaling B, we can arbitrarily define the hyperplanes that mark the margins. So instead of 0, we change it to +1, -1. So that's why in the movie that we watched on YouTube, they had, what was it? Bigger than or equal to +1 was inside of set C1, and less than or equal to -1 was inside set C2. Okay, so they're arbitrarily just choosing +1 and -1 as easy numbers to calculate, maybe, or like as a way to. So I guess from my perspective is, does 1 and -1 matter? Could it be 2 and -2? Could it be 3 and -3? Probably. Yeah. Hey, thanks so much, man. It's 3 a.m. Oh my god. Go to bed, man. Hope you have a good rest. Oh yeah, anytime, man. I'm following now, so now I know when you're on. I'll have to get something set up in the elements for you, so we get. Well, no, you're on the calendar, so I know when you go online now because you're on the calendar, which is great. So by changing your blah, blah, blah. So the distance between these margins is given as 2 over length of W, where length of W, here it is. So length of W is a sum of squares kind of thing, right? It's the sum of the squares of the components of vector V or a vector W. Why do they have negative signs here? That freaks me out. These should be in brackets. On the hyperplane that maximizes this distance. We need to minimize the magnitude of W while ensuring that each case is classified correctly. The algorithm does this by making sure all cases in one class lie below and all cases in the other class lie above. Right. A simple way of doing this is to multiply the predicted value of each case by its corresponding label, making all the outputs positive. Yeah, here it is. The margins must satisfy this. Yes, we have the return not fine. So it tries to solve the following minimization problem. Minimize the magnitude of W subject to this. Okay. Interesting. Right, so in the illustrations we've seen the classes have been fully separable. This is so I could clearly show you how the positioning of the hyperplane, blah, blah, blah. So what happens if it's not? I know, this is the exact question you were asking, right? So the original formulation of SVM uses what is often referred to as a hard margin. If an SVM uses a hard margin, then no cases are allowed to fall within the margin, right? This means that if the classes are not fully separable, the algorithm will fail. This is, of course, a massive problem because it relegates hard margin to handling only an easy classification problem. As a result, an extension to the SVM algorithm called soft margin is much more commonly used. In soft margin, the algorithm still learns a hyperplane that best separates the classes, but allows cases to fall inside the margin. Oh, interesting. So the soft margin SVM still tries to find the hyperplane that best separates, but it is penalized for having cases inside the margin. How severe the penalty is controlled by a hyperparameter that controls how hard or soft the margin is. Oh, interesting. The harder the margin is, the fewer cases will be inside it. That makes sense. Okay. The softer the margin is, the more cases will be inside. The hyperplane will depend on a larger number of support vectors in that case. This has bias variance trade-off. If our margin is too hard, we might overfit, whereas if our margin is too soft, we might underfit the data and learn a decision boundary that does a bad job of separating the classes. Fair. Yeah, check this out. This is cool. I like how they drew this. This is really cool. So far, the SVM algorithm, blah, 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 but I mentioned that one of the strengths of the SVM algorithm is it can learn decision boundaries between classes that are not linearly separable. Right, so in this case, it's going to be learning a curve. Right, it's going to learn a curve that's going to separate this stuff. Yeah, so here's the picture, right? So it can't find a line, so what it's going to do is it's going to go up into the next dimension, find the hyperplane, that hyperplane that where it cuts the kernel will give us the decision boundary. That's fucking cool. I think that's fucking rad. That's really cool. So I guess the question is, like, how in the world do you do that? Right? How do you pull that data out, right? Like, so it says data with a kernel. Like, what does that mean? It's pretty cool, though. So, yeah. So they're using a linear kind of thing, cutting the surface, and then projecting that intersection back down into the original dimension of the data. Cool. It's super sexy, yeah. Interpolate the number of neighbors in an epsilon ball. Ooh, that might, yeah, maybe. Yeah, maybe. That's not a bad thought. Okay, so they say the extra dimension is called a kernel. Why is it called a kernel? May confuse you. It has nothing to do with the kernel in computing or kernels in corner fruit. Well, I figured it wasn't kernels in corner fruit. In 1904, a German mathematician named David Hilbert, what a Chad, published this book that I don't even want to attempt to name. In this book, Hilbert uses the word kern to mean the core of an integral equation. In 1909, an American mathematician called Maxime Boucher published an introduction to the study of integral equations, in which he translates Hilbert's use of the word kern to kernel. The mathematics of kernel functions evolved from the work of these publications, and the kernel name has come along with them. Interesting. So how does the algorithm find this kernel? That's my question. It uses a mathematical transformation called a kernel function. There are many kernel functions to choose from, each of which applies a different transformation to the data and is suitable for finding linear decision boundaries for different situations. Huh. That's really freaking cool. Kernels in computing, like the Linux kernel? I have no idea. Too many different meanings for kernel in math. I know, I always think about the kernel as, what is it? Isn't the kernel like all the vectors that get sent to 0 or something like that in a linear transformation? So I'm thinking, oh, kernel, like that must have something to do with like all the things that get mapped to 0. Linear, I know, I'm such a linear algebra Chad. Damn, look at this. The sigmoid kernel, damn. The type of kernel function for a given problem isn't learned from the data. We have to specify it. Because of this, the choice of kernel function is a categorical hyperparameter. Oh, nice. Okay. Therefore, the best approach for choosing the best performing kernel is with hyperparameter tuning. Son of a bitch. So here's a couple of... Oh, so this would solve the problem that I was worried about. Radial basis. When we know that there's like weird blobs, right? So like this would need a radial basis one, I assume. Because it would have certain blobs it would need to take care of. Okay. I wonder what sigmoid does. Oh, sigmoid gives me basically separation. Like a wave or something like that. Right, so it would intersect twice. Yeah, okay, I can see that visually. I think the kernel of a map between groups is the same in abstract algebra. A set of things that map to the additive identity. Yeah.
Waits the transform,
Yeah.
e.g. Fourier's exp AOT. It's the operator's matrix element. Convolution becomes multiplication. Zeta, clean.
This is cool.
Laplace.
This is SVM shit. It's cool.
Eigenfunctions.
I kind of want to like play around with it with a data set now. Like I'm excited to do some of the coding for SVM when we get together next week. This is where SVMs become fun, difficult, painful, depending on your problem. Computational budget and sense of humor. We need to tune quite a lot of hyperparameters when building SVM. This, coupled with the fact that training a single model can be moderately expensive, can make training an optimally performing SVM take quite a long time. Ooh, okay. We'll have to keep that in mind when we go to start coding next time. We might have to answer questions while SVM is running in the background. The most important ones so the kernel, the degree hyperparameter, the cost controls how hard or soft the margin is, the gamma hyperparameter, which controls how much influence individual cases have on the position of the decision boundary. Cool. Okay, let's take a look at this. I'm getting pretty close to my limit of what I want to read. This is cool though. This actually gets me super hyped to try to do some of this next week. So the impact of the cost and gamma hyperparameters. Larger values of the cost hyperparameter give greater penalization for having cases inside the margin. Larger values of the gamma hyperparameter mean individual cases have greater influence on the position of the decision boundary, leading to more complex decision boundaries. There we go. Okay. Right, so as we increase gamma, we get more strict decision boundaries. So in other words, we start to overfit the data. And same with cost, right? As we start to increase the cost, the likeliness of overfitting the data is probably high too. Cool. Laplace. That's cool, man. That's cool. Okay, I think I'm gonna end her there. It's just about dinner time here. I guess the question is anybody online? Is anybody online and streaming tonight? Darth is on. X Lives is on. X Lives +5? Are they doing a Legend of Zelda run? That's cool. Is anybody streaming math right now, though? Let's just take a quick little peek and see. Oh, Something Original's on, too. Cool. There's some cool streamers on. No one's streaming math, though. All right. Since none of our streamer friends are streaming mathematics tonight, I think we're just going to call it a night. No math bio, big sad. It's all right. We were just suggesting content. Oh, gotcha. I mean, I'll still take a look. I'll take a look at it. I love this. Encoding overloaded. Consider turning down video settings. OBS is yelling at me because of this filter. It does not like my filter, but I like the filter. I think the filter is really cool. All right, boys and girls, it is time. I have to do it by Wednesday. Haven't started. Well, good luck. Good luck on the assignment. And thanks for swinging by. It was good to see you, man. Good luck with the new digs. Sick. And then you had to move. And you're starting up a brand new company. You're a busy man. Well, thanks everyone for coming and hanging out. I'll be back. When am I back? I am back tomorrow afternoon, actually. We're doing some gaming tomorrow afternoon. We'll be doing that with Sasha, aka the Collar Cone. That's going to happen around 2 p.m. Pacific time. We're going to be doing Legend of Zelda run. So hopefully we'll see you then. Next math stream is undecided. Probably happening next Sunday. No, I lied. Next math stream is happening Friday morning at 10. But I can't tell you what we're doing. It's a secret. It's super secret math stream Friday, 10 a.m. Be there. It's going to be a great time.
Look at this guy.
So, if I catch you during the week, we're going to be doing Zelda streams Monday afternoon and Thursday evening. If I see you there, awesome. Otherwise, hopefully I'll see you Friday morning at 10 o'clock for some cool shit. Until then, have a fantastic evening, morning, afternoon, middle of the night, depending on where you are. And we'll catch you guys soon. Have a good one. Take care. A good night.